Good morning, everyone. This is Shaun Darragh from the Lighting Design Lab. Welcome to our webinar this morning on commercial energy code for alterations. We are going to get going in just a couple of moments, allow a few more people to filter in on this fine, sunny Seattle morning. All right, good morning, everyone. I think that I am going to declare quorum. So once again, welcome to the latest webinar from the Lighting Design Lab, Seattle City Light. This morning's discussion will be on commercial energy code for alterations. Where are the areas in which the code is brought into effect for various building alterations and some of the things to think about. Before we begin, a couple of ground rules, a little housekeeping. During the webinar, everyone is muted. Sorry about that, but it's a little bit difficult to unmute people in this kind of format. I hope you'll understand. If you have questions, please go ahead and use the chat feature, or more accurately, the questions bar. You'll notice in your interface for the webinar that there is a little caret next to the word questions. If you click under that, go ahead and launch your questions. We will be monitoring them throughout the webinar. In some cases, we may stop the webinar and pose the question at the time. In other cases, we may defer them later in the interest of time. We are cramming a whole bunch of information into the next 2 hours, so don't be offended if we don't stop for all questions at all times. There is going to be one online poll in this particular discussion. Please go ahead and participate in it. And after the webinar, you'll have a very brief feedback opportunity. Please take that seriously. We really appreciate any kind of feedback that you guys have for these webinars. We're here for you, so the more you tell us, the more we can be. And this webinar is brought to you by the Lighting Design Lab. We're the platform. We are, of course, a part of Seattle City Light. We are powered by Seattle City Light. We are also very lucky to have Ben Roush with us from FSI Engineers and Duane Jonlin from Seattle Department of Construction and Inspections. Now, without further ado, I am going to invite Ben to introduce himself to us. Ben, take it away.
Yeah. So I'm Ben Roush. I'm a principal at FSI. I'm a dual licensed mechanical and fire protection engineer, and I run our high performance buildings group. Have a bunch of letters for certifications we need for various things. Most important bullet on here is code nerd down on the bottom. I really do geek out on these and the incentive structure that code set up, and particularly what's coming. I'll get a chance to tell you what I'm excited about here in a bit.
Thank you, Ben. Duane, over to you. Why don't you give us a little bit about yourself?
Duane Jonlin, I'm the Energy Code Advisor for the Seattle Department of Construction and Inspections, our building department, and my principal job is writing each new edition of the Seattle Energy Code, along with my many dozens of associates. that get involved in this and doing similar work at the state and national level. And my little comment on the bottom right there is just meant to say that I think what you'll learn during this seminar is that it looks scary from the outside, and people who've dived in already and started doing it are doing all right.
And what Duane hasn't told you is that many years ago, when we both had considerably more color in our hair, we were compatriots at one of the architecture firms in town with 4 letters. So for myself, those of you who don't know me, Duane convinced me to provide a slightly less stodgy intro slide for myself. So I'm Shaun Darragh. I am Senior Lighting Specialist at the Lighting Design Lab, also transitioning into a Senior Energy Management Analyst at the lab. I've been in the lighting industry for more than 30 years, doing everything from running design studios to designing theater to teaching. Currently, I predominantly teach at the Lighting Design Lab and also in the UW architecture department. And if I'm not doing these things, I'm usually out doing one of these other fine activities. So with all of that said, that's given a little bit of information about us. We're curious about you before we go ahead and talk to you. So if you would be so kind as to participate in this poll. The poll that we are looking for here is, please tell us a little bit about yourselves. Do you consider yourself to be a design ally, a construction ally? Are you in sales? Are you a facility professional? Are you utility or governmental? This will help us to have a sense of where some of you are coming from so that we have a good idea about who it is that we're talking to and how perhaps we may best tailor our remarks to you. 68% of you have voted. I'm going to give it just a couple more seconds here, maybe another 5 or 10. All right, I'm going to close this and I'm going to share the responses with you. So within this group, we have an awful lot of design allies, and we have some utility and governmental folks, but not a lot of construction folks, contractors, sales, or facilities people. That's very interesting. So I hope that this will prove useful for all of you as we go through this. Now, Duane, I am going to hand things over to you. So take it away, Duane. Give me 1 second. I have to close this poll. There we go. Take it, Duane. You should be set up as a presenter and ready to go.
Okay, let's hit show screen and see if that works.
We are there. Looks good.
So as Shaun mentioned, we got a lot of, hello, I want to have that slide up, not my face up here. Hello. Are you all seeing the slide or me?
We're seeing both. If you don't
want
the
slide.
If you don't want to be seen with your slide, just turn off your camera.
All right, that's fine. I just want to make sure you can see the slide. Okay, so as Shaun mentioned, we got a lot of stuff to cover here, and I'm going to I note on the trail map. I decided to switch from having a road map to being something more sustainable. So we got a trail map here instead, that Pacific Crest Trail. I've highlighted on the bullets on the left, Ben and Shaun. That's the center piece of this. So I'm going to buzz through code requirements pretty fast because I want to get to them to talk about, okay, how do you deal with these code requirements in an intelligent way. So you can see those first few though are me. We're going to talk about big picture stuff and some general rules, and then I'm going to go through really quickly the code requirements for HVAC before Ben starts to tell you how to make that happen. With all this, now it went away again. Okay, with all this code requirements for existing buildings, we've got a much more challenging job because we've got to meet these big targets. With new construction, you know, it's relatively easy. You just go in there and make those code things happen in your new building. With existing construction, where you've got space constraints and of course budget constraints and every other kind of constraints, it's trickier. But this is like the general Seattle diagram I made several years ago, and that vertical dashed line is kind of relentlessly moving to the right. The idea was going to be that we would shrink continually our fossil fuel. We would, as best we can, grow our existing renewable energy, and then that top triangle in white is got to all that has got to be accommodated with efficiency. It is possible, but it's really tough. And given that we're doing fine with existing buildings, but we're having a rough time. I mean, we're doing fine with new construction. We're having a rough time with existing buildings. This is going to be a challenge to get a huge amount of savings out of our existing building stock, but that's where we're going. And Seattle's got these things baked into the climate action plan, and every year we've got to send a progress report, each of us departments, to the mayor's office to say, okay, we are on track, we are off track. What happened a few years ago is that we realized that building emissions from buildings were going up because of the huge construction boom. So that explains the number of the code changes that we've just made. So if you're doing an addition to a building, which could go out, usually goes out horizontally, but could be vertical like this one, you have your choice. The addition comply all by itself with the new code, or the combination of the addition and the new can comply. And just about every addition, if you're larger than 500 square feet, is going to talk about having to actually do the C406 additional efficiency options as well. And by the way, I should say, today we are talking about the commercial part of the energy code. So not houses, not townhouses, and not low rise like 1 to 3 story multifamily, but everything else. In general, when you're doing an alteration, stuff that was built back in 1942 or whatever that met code then can usually stay just like it is pretty much forever. You can fix things, you can service things, but anytime you put in something new into the building, the new stuff has to meet code. We're very careful about anything that Landmarks Board says don't touch this, we don't touch it. And we have some discretion in the building department. When people have these impossible situations, we can work with you. What I heard from a lecture a long time ago about this same topic was, well, don't come in empty-handed. If you want to come in and say, we really, really don't want to do X because it's going to be just crazy, come in with something you're going to do instead that's going to save energy for us. So there's a few situations where you got to bring the whole building up to code or very close to it. And Seattle, everybody loves substantial alterations. That is usually defined as substantially extending the physical or economic life of the building. So a big gut and remodel, or even just major overhaul of 2 or more big systems in the building. But also change of space conditioning. Usually that's from warehouse type thing to conditioned. And in Seattle, that's also from heated only to heated and cooled, but see the asterisks there. Also change in occupancy from something funky like a factory or a storage building to something else, and a couple others switching back and forth between dwelling unit and non-dwelling unit. The exceptions in the red box there are that for any of those, you can have you could have the envelope UA be 10% higher than we would permit for the new code if everything else inside meets current code. And for substantial alterations, that's actually 15%. Or if you're doing energy modeling, then you could have that overall emissions be 10% higher, because there are just some things in existing buildings you can't get all the way to code. You do have to get C406 credits. Now, if you're doing a subalt, then we're saying this is pretty much a new building. So if it meets that substantially extend the life of the building, or it's vacant for more than 24 months, you're going to go there, and we're going to like work with you on calling it a new, not just for energy, but also for seismic and life safety. There's a number of exceptions, different ways to go through this that I'll be happy to talk about with you if anybody wants to bring a project into me. If it's a TI in a new building, that first 18 months after we give the C of O for the shell and core, you can use the old code. Just keep that in mind. Now, the interpretation I mentioned a little bit ago is that, remember, if we transition from heated only to heated and cooled, we're calling that a full building upgrade. An exception that we just published on our website is that if you're going to go from some system that is going from a conventional electric resistance or fossil fuel system to a heat pump heating, which inadvertently adds cooling, and you can do a model or a calculation that we'll accept as being legit, that shows that even with the added cooling capacity, the overall annual carbon emissions is going to be lower, then you're good to go. We've now done this for a few buildings where they wanted to switch to heat pump. It's going to be way more efficient, and they could show that even when you add the cooling, we're not in any worse shape than we were before. I wanted to mention, we're talking right now about the current code, the 2018 code, but the new thing that just passed for commercial for the next code, which will go into effect, that 21 code will go into effect in July of 2023 statewide. They are going to take that Seattle heat pump rule and for alterations and put it into the state code. So with a number of exceptions, you'll be required to go forward. However, they built in so many exceptions to the state code that I don't think that many alterations projects are going to end up having to convert to heat pumps under this next code. New construction, yes, but not this. In general, in Seattle, if you replace any kind of central heating system, the new one's going to have to be heat pump. And we have this big exception at the bottom that says if there's one failing piece of equipment, you can replace that like for like, because it's cold out, the apartment building needs heat. We're not going to make you go through a whole design process, and people are using that right and left, but that really is not for any kind of planned replacement or larger project. It's just something fails, you have to replace it right then. We'll let you do it without converting to heat pump. And we know it's a problem. That stuff in the red box is all the issues that people are up against when they try to convert over. But if we don't take this opportunity for when you're already converting something to a new piece of equipment, if we don't use that point to move to heat pump, then there really doesn't seem to be any other more economical way to do it. So we know it's that owners are not interested in this in this kind of upgrade. Most people are not in business to save energy; they're doing other stuff. But it's tough. So that's how we've settled is at that point of changing out your HVAC system, you're going to go forward. PACE financing, property assessed clean energy, is now available, and I think Ben's going to mention this as he goes forward. That it's typically we've seen it only allowed by lenders for very large projects, but Ben says he's got some evidence that more modest upgrades would be available. So there might be some financing options in King County that didn't used to be there, and a couple other counties in Washington State as well now. Well, Ben's going to get into cooling system alterations, but basically we've had this in place for many code cycles that we're very economizer dependent in our HVAC part of the code, and so when you're adding cooling, you gotta either have a DOAS or an economizer system, and then the economizer has this very complex long table that gives you lots of options for doing higher efficiency equipment in place of doing the economizer. The TSPR, this new total system performance standard, is typically not required for alterations. Those same exceptions we just mentioned, the change of occupancy, change of space conditioning, subvaults, and also if you're just replacing your HVAC system, you would have to do the TSPR calculation, but otherwise not typically for an alteration. For commissioning, it's going to follow similar to the rules for new construction, that if the work that you're doing impacts a system that is over those limits, then we will ask you to do commissioning on those limits. I should mention that commissioning has not been evenly enforced in the past, and there's been some management changes here at the department, and commissioning will be required, and please make sure that your projects have that in the contract documents and budgeted for construction, because it's just about to get real right now. So one last thing I wanted to mention before we go forward into solutions is that Washington has the Clean Buildings Act that is starting to kick in the next couple of years for buildings over 50,000 square feet, and legislature just passed rules that is going to start filtering that down to 20,000 square foot buildings that need to meet a particular energy use target or pay this fine, $1 a square foot a year. Seattle is just embarking on doing its addition to that building performance standard idea by saying, well, we will have these EUI targets that should probably stay the same as the state, but also carbon emissions standards. So we're developing those right now. And this is all to say that if you're looking at these big buildings in Seattle or elsewhere in Washington and trying to decide, okay, our old building is not meeting this current new standard, what do we do? I don't think anybody's going to want to replace the facades. So your real big option for both the CO2 and the EUI is going to be change over to heat pumps. If you're doing major work in a building over 20,000 square feet in Seattle, I would suggest strongly that you have a heart-to-heart with the owner about how they're going to have to do this anyway really soon. Might as well do it now. We also have a Tuneups program just to make sure that every 5 years at least, if you can't demonstrate that you're doing some kind of continuous improvement system, you got to go through all the energy using systems. You got to fix the easy and obvious things. You know, if there's a dead relay or if there's a persistently wrong setting on something, there's pipes you find that weren't insulated or whatever, those all have to get fixed. You don't have to do big capital improvements, but you got to fix the things that you find that are wrong. And that's starting already phasing in. So we're going to switch over to Mr. Ben.
Duane, while we're doing that, there is a question. Is C406 the part of the code that requires all the efficiency upgrades and switching off of gas? And while that's being done, Ben, I'm going to make you a presenter.
So C406, I'm sorry, I forgot to even introduce that, is the part of the code that for new construction and for some alterations, so major alterations, requires that we do that we add a number of above code things to each project. And so C406 basically says that along with doing whatever you're doing, you have to go through this list of options and pick a few to satisfy the requirement to do a few above code things.
I want to tag in on that too. So what specifically requires building heating over to heat pumps and building service water heating over to service water heating are in their respective sections. C403 has a section right up top, and C404 has a section a few down. So HVAC and service water heating, C404. But you get bonus points out of C406 some of the time. All right. Hey, I'm Ben, I'm back. I wanted to take a brief moment to say what I'm excited about and also modestly interested to see what questions come through. I think it's impossible for any one person to hold every if and therefore of the code in their head. I do my best to memorize the code every code cycle. Some people in my office think I actually managed it. Absolutely not true. And so I'm excited that we're all practitioners here. And some of the time I'm going to have to look up the answer. I'm going to tell you what I know, what I'm excited about. The thing I'm most excited about is that we are moving towards building electrification and a whole lot more heat pumps. So I'm going to say heat pump or some variation on heat pump so much today. All right, that should go to the next slide. Give it a second. So this is my agenda, and it's HVAC focused, and then I'll do a single slide on service water heating. It's a little more straightforward. And we're going to break this out the same way most mechanical engineers think about it, into air side and water side systems, which is air side and hydronic, would be another way to say that. So Washington and Seattle, they continue to be at the forefront of code development. And of course, the big change and the one that we're all buzzing about is the electrification provision. When you're living in Chapter 5, all that it really says is go back to C403 if you're replacing the HVAC system. Like Duane said, there's some provision for I need to replace a part. And the Washington code in this next cycle is going to have some provision for I need to replace this thing, but it's so difficult, I need, you know, a more electrical service. I'm actually going to give you a note on that in a bit. I'm trying to say this more than once. We've had to, in Seattle projects, we've had to replace the electrical service twice now, and it was less than 2% of the construction cost, both times, 2%. So it's a pretty modest cost compared to the whole, you know, those are major building retrofits. It's you know, beyond a TI. But still, it's not a giant portion of the work. So we'll see how much that actually limits the Washington version, or how much heat pump we can actually squeeze in, knowing that if buildings already had AC, they might already have enough provision for heat pumps, particularly as they get better at the low temperature. All right, so broad overview. Again, you break it, you bought it. If you're replacing the equipment, you are gonna meet all of the provisions of C403, the mechanical section, C404, and C405 that Shaun's gonna talk about. So TSPR in existing buildings. So total system performance ratio, and I think Duane had a brief slide on that. It's the carbon impact and your system HVAC loads are the denominator and numerator respectively. So if you are working in an existing building, and if you are only replacing the HVAC systems without thinking about the envelope, TSPR could be a sticky problem for you. We have done this a couple times and had TSPR be a real squeaker even when we did systems well above a code minimum, particularly if those systems had gas heating in them. So if you're keeping the existing envelope, you need to get on that early on. There's a solid chance you actually need to improve the envelope just to get a compliant TSPR. And there are some provisions for if you don't like TSPR, but generally speaking, if you're one of the occupancies required for TSPR, which go look in the code, but it's about the same as the occupancies that required for DOAS in the previous version. So you should be fairly familiar. It's going to push you into it. Bit of a thing. Otherwise, from chapter 5, you get the equipment economizer exceptions that Duane said. You get and there's some capacity limits on that. Again, you really have to treat even tenant improvements become a little bit more of a whole building issue as we start having required DOAS, required TSPR. All right, so I broke some of these down and I'm starting with the most likely systems to the least likely systems. So there's a tremendous number of variable air volume, VAV systems out there. Rooftop unit and some sort of VAV box with reheat coils. So this is straight off train trace for those of you who are using it. So this is the rooftop unit, preheat, cooling, and then secondary with a reheat coil. It's a parallel box or series box or just a pinch box with reheat. There's a bunch of ways to get that done under the more modern code. There's fewer ways to get that done. But these heating coils, of course, could be gas by way of a boiler. We'll talk about that in hydronic. They could be gas by way of a gas furnace section on the rooftop unit and then electric reheat. If DOAS isn't required, you're allowed to keep that VAV system. There's a question mark. TSPR, every TSPR occupancy is going to require DOAS. So if you didn't require DOAS, chances are you didn't require TSPR. So you probably are going to be able to just replace like for like. However, you have to look at if you've got gas in your system by way of that boiler or gas furnace, are you moving to heat pumps? Duane said for Seattle, you should seriously look at doing that conversion because we're going to head for a zero carbon world where we're counting on everything being electric. It's worth saying that Washington has, a similar BEP standard, all of Washington, and on those targets, I expect electric to get better and better while gas essentially stays the same. It's emitting that much carbon forever. So in a future-proofing way, we probably want to talk about moving things to heat pumps, even if you don't expressly have to under this version of the code, or if you could use one of those Washington exceptions in the next version of the code, you might still want to do it. There's externalities beyond just meeting the code right now. There's that future ratcheting down BEPS targets that heat pumps will really help you over a gas system on an EUI target because they are 3 or 4 times more efficient. Okay, so VAV systems, you might need to do a heat pump on the rooftop, and you are allowed to have electric reheat in the boxes. Of course, Washington is going to allow you to just keep terminal units the same. There is a provision even in the Seattle code, the current way it's written, that you get some electric heat for heat pumps for low temperature ambient operation. So it's possible you're going to be able to keep that VAV box coil and use it for low ambient operation. There's quite a lot of math that goes into it to see if you've maxed out your capacity or gone over your capacity limits for the exception. If you don't like it, you can also talk about high performance VAV. We'll talk about it on the hydronic side. So Shaun, I'm still not seeing questions. If they're coming in, just call them out because I want people to ask as we go.
I will let you know, but this is a good reminder. If you do have questions, please go ahead and enter them into the questions box. I am here and I am monitoring them. Ben, I'll let you know when they come through.
Perfect. Hey, it's the same image, only DOAS would be required. So these are the occupancies, you know, the school's office. Now assembly was just added. You can keep going down that list. That requires DOAS with energy recovery or heat recovery at various effectiveness, depending on if you're in the Seattle or the state code. So if DOAS is required, you've got a gas pack rooftop unit that clearly isn't going to stick around because you need energy recovery. You've got the secondary box fans that no longer meet the requirement to do secondaries, you know, supply the ventilation air separate from the local conditioning air. And the obvious heir apparent here is going to be VRF style systems, moving refrigerant around buildings. I'm going to give you a good note on refrigerant in a minute, though. And then replacing that rooftop equipment with a DOAS unit with ERV or HRV, heat recovery or energy recovery ventilators with the appropriate effectiveness. The nice thing is that your ducts will be oversized. Your main trunk down an existing building would be oversized in that VAV unit. It would have been sized to do all of the conditioning with air. And your new DOAS unit will only need a small portion of that duct. You can either reclaim it or you can just have a really low pressure drop duct. You'll be reworking interior, you know, plenum spaces because you'll need, you will have the ductwork supply out for ventilation if you continue to use the VAV ductwork, but you will need some secondary ductwork for the local conditioning, heating, cooling equipment to divorce them. If you don't like that, there is an alternative. There's an exception to C403.3.5.1, the DOAS requirement, that you can do high performance VAV. They used to be right side by side in the last version of the code. They now live in a separate section, but you can go find it. And it's much the same. It's got a list of, I think, 16 measures that you must meet. It's going to require a state-of-the-art control system. You will definitely be replacing, you know, if your building is more than a couple years old, you will be replacing the control system. One of the, either the heating, including the box heat and the RTU heat, or the cooling system have to be hydronic. And we thought we were going to do more high performance VAV when we got that provision in the 2015 code. And honestly, we have done, I think, 2 of them. And we did them on the chiller side. So we had a chiller connected to the rooftop units. It limited the hydronic side. It might be an easier to change out, but again, the heir apparent is going to variable refrigerant flow with a DOAS unit and reconfiguring your system. And that DOAS unit ideally would be a heat pump, not with gas preheat. So you're set up for an electric future. All right. Duane mentioned this briefly, I'm going to mention it again. So the economizer, if you're going to keep a VAV system, I should define an economizer. I won't assume you're all mechanical engineers. So basically, it gives you the ability to bring in outside air up to 100% of the flow of the air handler to get quote unquote free cooling. So when it's 62 degrees outside and you need cooling in your building, most of the places, particularly the high solar gain side, you are essentially getting that cooling only for the cost of fan power. You aren't running mechanical cooling. So there's a question, particularly for built-up air handlers in some older, tall buildings. The answer was no, you didn't have an economizer. Energy was cheap and they didn't worry about it. From buildings from, I don't know, the late 80s on, I would expect you have an economizer most of the time. If you don't have an economizer, well, you should be looking at putting in a DOAS unit so that you don't need to put an economizer if you have limitations on that. If you can't get to an outside wall, it's really hard to put a larger duct to an outside wall. You don't have enough air intake room. You aren't actually on the roof level, you're in the basement. There's all sorts of reasons it could be difficult. Your option is in Chapter 5 to either increase efficiencies or have partial economizer plus some efficiency gain. Your other option that really isn't stated out in Chapter 5 but is allowed is to do a DOAS with energy recovery or heat recovery and then you don't really have anything more than ventilation air going to the space. So you can go back to that again. All right. So fan coils, VRF, and the meaning of life, which for the Douglas Adams fans out there is obviously 42. So fan coils, we typically think of them as 4-pipe fan coils. I have a heating coil, a cooling coil, and a fan. And in some cases, an outside air intake, direct connected to it, or sometimes they were already set up with DOAS units. Back in the day, you might have had just a true DOAS unit, no return, no exhaust, no energy recovery. It just pumped 100% outside air into the building. So you got to start almost any mechanical system replacement once you determine, yes, I meet the provisions of Chapter 5, I've replaced enough, which is to say more than one portion of the equipment, like one boiler, one air handler, so on. I've replaced enough that I am going to have to meet C403. You got to go back to the top of C403 and say, does TSPR count? Does DOAS count? So for fan coils, for those hydronic things, you might be able to keep that hydronic in place. We'll talk about what you have to do on the hydronic side when we get down there. You might also replace them with VRF again. It's a really flexible system that is making retrofit a hair easier in most cases. The exception being extraordinarily tall buildings. VRF has a height limitation. You can only go up 8 or 9 stories and down 10 or 11 stories. And that has to do with the refrigerant and how hard the compressor's working. Again, you got to go look at, did you already have energy recovery? In some cases, you might have. On VRF, we also have to ask, why are you replacing your VRF system already? It's a new enough technology. Did it really fail already? And you kind of got to go looking harder at that. I promised a refrigerant note. So our fortunate, go ahead.
One sec, is this a good time to ask another question as you're transitioning between?
Yeah.
So this goes back a little bit to, related to slides 5 and 6. Perhaps you mentioned that are these 2021 code requirements or in current code if one wants to convert the existing system to heat pumps?
Yeah, good question. So we're in an interesting code environment right now. Seattle has an all electric requirement. So if you're touching a system in Chapter 5 as an alteration, and again, if you're doing something more than an emergency repair, you are gonna move it to heat pumps in Seattle. Right now, the 2018 codes for Washington do not have that requirement. You can keep your gas heating, again, with the caveat that the energy use intensity targets, the energy use per square foot per year targets of the building energy performance standards are going to continue to ratchet down. And you're very well served to look at, did that building meet that BEP standards that you're going to have to meet in 2026 through 2028, 50,000 square feet and bigger, and it actually goes from the biggest buildings, and the 2028 is the 50,000 square foot version. But you're best to look at it now. If you're doing a system replacement, you might be able to solve it in one fell swoop by moving to a heat pump. So that's today's code, the 2018 code. In 2021, Washington State is going to have a requirement that all new buildings are heat pump based, no gas for, again, service water heating and space heating. You'll still be allowed to do industrial uses and other non-regulated uses. I think I'd say it that way. And in Chapter 5 of Washington State Energy Code, this is new news. This happened, I think, Duane, a couple of weeks ago, that the State Code Council adopted the recommendations of the advisory group and are going to have an all-electric provision for new buildings again, but also Chapter 5 for alterations is going to push you into electric buildings, except some pretty broad exceptions. So added electrical service where it's infeasible, where you've got existing hydronic systems. There's some pretty big holes in the Washington code. I think that was the whole picture. That'll take effect in July next year, and then I would expect the Seattle version of it in January of 2024. It's a pretty standard code cycle we've been under. Shaun, anything else for questions?
Thanks, Ben. Nope. Proceed, please.
All right. So VRF, we can't say VRF over and over and hey, it's this flexible system and it works pretty well most places without saying two things. One, ASHRAE 15 is a standard on refrigerant concentrations in rooms. So VRF works by having refrigerant instead of fluids or air to move energy around. And as such, it's got really large refrigerant charges. For some of the biggest systems, it's hundreds of pounds, truly hundreds of pounds. So if you release that volume under a catastrophic leak into a small space, it displaces oxygen. And so ASHRAE 15 gets into some real technical specifics. You should be requiring it on every one of your projects. And if engineers in the room, you should be doing the math on every one of your projects to make sure you don't have an issue, particularly in, we particularly worry about that when we have sleeping compartments, residential or otherwise, or truly, a non-mobile population, hospitals, nursing homes, and the like. We have a long discussion about that with the owner every time. So, first one. Second thing to know is that R410A is on the chopping block. R410A is our go-to refrigerant in commercial refrigeration. R407C is also on the chopping block, similar mix, but for more like the refrigerators and refrigerated cases of the world. And the reason is in this graphic. On an index value for where CO2 is a global warming potential of 1, a pound of CO2 is a global warming potential of 1. R410A is the global warming potential of about 2,000. And you can get numbers that are slightly lower and slightly higher depending on how long of a time frame you look. So these are 100-year global warming potentials. On a 30-year basis, it's like 1900 something. The obvious thing that we're moving to is what some Asian markets have already moved to, which is R32. And it's a beautiful refrigerant. It's actually R410A is partly made of R32. But R32 is very mildly flammable, is the way to say it. It's at a concentration of 12 or 13% in the environment, or another way to say that, it's 120,000 parts per million. It can be flammable. Of course, once you pass 35 or 40,000 parts per million, it was already toxic because you displaced all the way too much oxygen for humans to survive. But we don't have a building standards that recognizes it yet. I know code councils are hard at work on that, and Washington and California have a pretty aggressive target on when this phase out is going to occur. So there might be a period in here where that equipment can't be sold. We're going to see. Mitsubishi sent me an email last week that was just really good timing. They're coming up with a hybrid system that does refrigerant to the switching box, the branch controller, and then does hydronic, so you can run hot water or cold water out to the individual rooms, which should, at least in theory, drastically reduce the amount of refrigerant in the system. And maybe it makes R32 work better if those branch controllers are in very large rooms. It makes that leak so much less likely to actually build up to that flammability, lower flammability limit. All right. So that was your side note. Last thing. A couple other systems, a little more oddball. Water source heat pumps, we'll talk about this more in the hydronic, but you got to look at, again, TSPR required, DOAS required with ERV, which they aren't really set up for a lot of the time. Do you have a gas or electric boiler? Most water source heat pumps had a cooling tower, not a chiller. So, and there are some fluid cooler requirements out of C403. But if you've got water source heat pump, and that was kind of the go-to for extremely tall apartments is where they're mostly used now, but has otherwise been a go-to in the past for all sorts of things. So you might choose to keep it. It's a effective system, particularly if you can get the boiler to something else. And the hot, when it's running in heating, it uses, a 2-pipe supply return. but when it's running and heating, it might go all the way to 90 or 100. So it's a really good 90 or 100 degrees maximum on the loop temp. So it's really good for heat pump chillers. We'll talk more about that in a minute. Last one, the first time I saw a dual duct system early in my career, I went back, I took a bunch of pictures, I went back and told my boss that this was a messed up mechanical system and I couldn't follow it. That was Michael Eshelman. He thought that was very funny. A dual duct system has a hot deck and a cold deck. So it's got all the way hot air and all the way cold air, and it mixes. And so in the code now, there is a solid provision. You can't simultaneous heat and cool, except with some extremely limited provisions built around variable air volume systems where you slightly overcool and slightly reheat, but have to temperature reset and a bunch of stuff. So great. If you've got an existing dual duct system, we have run into this at some of the King County buildings downtown, where it's big tower, we're not going to change it. And you have to figure out how to limit where it doesn't heat or it doesn't cool some of the time by way of controls. So you've got a neutral deck and a cooling deck, or a neutral deck and a heating deck. And it's kind of a pain, honestly. But it can be done. You can work your way around it. Of course, it's not going to meet any sort of energy recovery requirements. If you have to go there, you're going to be looking at system change out. On the plus side, if you have to do a system change out, there's 3 big ducts. So you've got a hot air duct, the cold air duct, and a big return going back to the unit. So you have plenty of duct already in that building to do your DOAS, direct air supply, and then your return for energy recovery. And then again, you're going to be looking to something else for the terminal units, you know, VRF, hydronic if it already had hydronic, so on. Last thing, there are difficult occupancies, and in C403 there are some occupancy specific things around hospitals, labs, some high occupancy spaces. They can be really difficult in a retrofit situation. And so you've really got to go reading, particularly down in the lower parts of C403 where most people have already tuned out. And again, particularly what we run into if you're going to go all electric, again, in the next code cycle for Washington or in this code cycle for Seattle, the high air exchange occupancies can be a real problem for heat pumps. If you've got a very cold entering temperature on a heat pump, it can be an issue, or you need a very specialized heat pump. So there you go. Moving on to hydronic, Shaun checking in on questions before we move on.
No questions, but a good reminder, if you have questions, please go ahead and enter them into the questions box.
Perfect. All right, so I'm going to start with easy. Easy is nice. So chillers, if you're replacing your chiller, it's electric already, although I did see a natural gas powered chiller and was kind of aghast at that. Get it? Never mind, I'm sorry. So it's pretty easy. You need to meet the new efficiency values. Heat recovery chillers don't have industry standard ratings yet, so that's a bit of an interesting one, although the industry is kind of coalescing around specific efficiencies. And you, of course, with that economizer exception from chapter 5, you might need additional chiller efficiency that then you can necessarily get on the open market. And then for specific uses, you have some need for a specific efficiency raises over the base in the table, the base value in the table, or for some specific occupancies, you have some heat recovery requirements that could require specialized chillers. Boilers, less than 140 degrees, which is what we think of as condensing boilers, which, you know, the flue gas condenses and you get more energy out, somewhere between 93 and 96% efficient to the conventional boiler 80%. So question 1, why are you already replacing your condensing boiler? The first condensing boiler I can remember putting in is in 2005. So maybe it's time to replace it, but it should have another 5 years or so on its life. But if you're doing it, and you're doing it because you have to go to electric, the obvious thing to move to is a heat pump chiller. 140 degrees is about the maximum they can make right now, and they have capacity issues at very cold temperatures. Sorry, I think my headset just got taken over. And they've got capacity issues at very cold temperatures. So it might require an electric backup, which again is code allowed. But as soon as you do that electric backup, you are really looking at electric capacity of the building, adding electrical service, which again has been a more modest cost than what we thought. You know, we got both the projects we've had to do it. We got the warning early on that it was going to kill the project, it was going to be horrible, and then it ended up being a couple percent of the total construction cost. But still, it's a couple percent, it's nothing to sneeze at, and you got to know that that is a possibility that you're going to need to bring in another additional electric service or a larger electric service. Also consider that the heat pump chiller, once you start doing that, you need to talk about refrigerant. And like we said, R410A is going away. That R32 might work out really well because this is a closed contained small volume system. It depends on where this chiller sits. CO2 is actually an excellent refrigerant, but needs super high pressures, just really, really high pressures, tends to be more expensive equipment. But because of those high pressures, it also can work at lower ambient temperatures. It can solve some of that issue of needing an electric backup. So this is, you know, to the mechanical engineers in the room, you owe your rep a beer, and to the architects in the room, you owe your mechanical engineer a beer. No, I'm just kidding. You really need to get deep into your discussion with your MEP engineer, though, about what is the possibility of replacing this gas equipment. Going to something more difficult, 180-degree boilers, which was kind of where most older buildings run. If they don't have condensing boilers, they're probably running a 180-degree hot water loop around the building. There aren't heat pumps that can just go from ambient air to 180-degree water. They don't exist. So what you have to do is what's called a cascading loop. So you do an air to water up to 140, and then you run a closed loop to a water to water heat pump that lifts the other 40 degrees. And then you've got another loop running around the building that goes 180, comes back 160, gets lifted again. They're kind of finicky systems, and it is a difficulty to do this, but it does exist. It is possible. The coefficient of performance still approaches 2 even at cold temperatures, which is another way of saying it's 200% efficient, again, to the 80% efficient of the 180-degree conventional boiler. At 180 degrees, you probably, even if you were running a condensing boiler, you probably weren't getting any of the benefit of the condensing, or very little. Of course, you don't have to replace like for like. If you have a hydronic system, you don't have to keep it. You can talk about going to other options like, again, VRF with an energy recovery ventilator on the roof. You can do a whole system change out instead of just dealing with the boiler plant. If you're doing a major TI, you're probably considering that anyways. All right.
Yeah,
so the mechanical engineer, go ahead.
I have a question for you on that last bit. Can you, if people have the 180-degree boiler, is that just for that freakishly extreme cold day in Seattle? And would it be possible under more normal circumstances, like, you know, typical Seattle like today, that you wouldn't have to run the cascade, that you could just run it on a you know, with 140-degree water or something like that? Or am I dreaming?
Yes, that's a great question. Let me just advance this slide. So on a conventional boiler, you have to kind of run it at 180 degrees, or you have to run a little loop at 180 and run the main loop at some lower temperature, because it can't handle condensing. So if you get down below 165 to 170, depends on the exact boiler configuration, it starts condensing and it eats itself. So a new boiler can eat itself in a couple of years. So turning it down, turning the loop temperature down, yes, you can. You don't really get any benefit if you're a conventional boiler, but on a heat pump basis, yes, we definitely want to talk about that. And of course, on when we used condensing boilers, we would run 180 degree on the coldest and then turn them back down slowly. We, depending on the temperature of the day. We'd ramp them back down to 140, 135 on the warmer days of the year to get the peak efficiency. The main limitation to doing that is right here. So this will be particularly useful for mechanical engineers and maybe a modest education for everyone else. We've got heat exchangers can only get so much heat transfer theoretically. So a coil, a hydronic coil in an air handler is a heat exchanger. It's exchanging the fluid, the heat in the water with the heat in the air, or when you're cooling, it works the other way. The heat in the air is going into the heat in the water, going into heating the water. You know, you go back to your chiller and you cool down again. So that coil has very specific characteristics. It's so big, it's got so many rows of coils, it's got so many fins per inch. Those fins are these specific dimensions, and it's very, very hard. Even if you sat there and made your intern count how many fins per inch over this coil and the exact characteristics of it, and got your calipers out and started measuring, exact tube diameters, getting our reps to tell us, oh yeah, that coil has a capacity of X is very difficult. So if we don't have original design drawings or even better submittals that tell us what that coil was, what was expected, it's difficult to say this coil designed for 180 degrees on this this worst case day is going to work fine with 160 degree water, or is going to work fine with 140 degree water. What I can say for certain is that many very old systems, and we've worked in a lot of old schools with systems from the 40s and 50s, hydronic or steam systems. Those coils are massively oversized. They're way more capacity than that school needs, and you can get that in part by, if you've got a more modern control system, you know how far open the control valve opened. If the control valve never opened past 60 or 70%, you've got way more coil than you need. So there's a way to kind of back your way into, do I think this will work? Am I comfortable? Can I just arbitrarily turn the water loop temperature down? But you're not going to find many mechanical engineers who are like, yeah, go for it. It'll work fine, because there's so many it depends. The limiting factor for the ones who really want to geek out, log mean temperature difference. You can go look that up. But for a given log mean temperature difference and given entering conditions of water and air, you can only get X amount of heat transfer. And if you turn one of those down, the entering water temperature, the ending air temperature, you'll get the same heat transfer, you just get it at lower temperatures. It's a long way of saying you won't get as hot air coming out if you lower the water temperature. Anyways, that was deep, and I'm happy to answer questions on it if you got them. We got to talk about. Go ahead.
There's one actual comment here, which is heating coil replacement can allow low temp heat pump replacements.
Correct. Yeah. So if you've got particularly built up air handlers, coil replacements make a lot of sense for that large system. You can replace all your terminal equipment. You could keep your air handler fan and just replace the coil. You could replace all the radiators. You could keep going down the line. And this is in the hydronic world. The only thing I can go, woo, you get to keep the pipe. So you replace the heat making part and you replace the heat rejecting part, but you get to keep the stuff in the middle. If it's in adequate condition to be worth keeping. That's a big caveat of its own. But yeah, you can absolutely, if you've got a simple system, you can replace the coil, or if you've got a very complex, expensive system, like a built-up rooftop air handler that you're trying to keep most of, you can just replace the coil with one selected to 130 or 140 degrees. And honestly, with a heat pump chiller, I'd select to 130 or maybe even 125 so that I could run down to very low ambient, maybe not need the electric backup. All right, we got to talk about high temp water and steam. Similar to that dual duct system, the first time I saw a high temp water system, boiler sitting at 220 degrees, but it was hydronic instead of steam, I had a real head scratcher. So that was an early career learning experience. They're super rare. They were really done in, I think, the late 80s to the early 90s, but they do exist. So if you've got a boiler trying to make 220 degree water, obviously a heat pump won't get there. and even a cascading loop heat pump probably won't get there. And then of course steam, 15 psi steam, 230 some degrees or higher, isn't gonna get there with a heat pump on its own. You can do electric resistance. Your energy will cost 2.5 or 3 times more and won't really meet the provisions of the code that require a heat pump. So if you've got a steam system, you can limp it along for a while, replacing one boiler every 2 years, a la Seattle, or in Washington State, you're probably going to get to keep it. But otherwise, we're kind of at a loss. What I've loved seeing recently, and they're more experimental than mainstream right now, but I've seen some an air to steam heat pump for residential scale. That was, I think, Weissman. I'd have to go look that up. And then Siemens and Fuji Electric are making wastewater heat recovery to steam products. So they can recover not low-grade steam. They expect reasonable temperature, or not low-grade heat, but reasonable temperature heat. I expect there's one plant in Germany that's doing sewer heat to steam. So they're doing district steam off of the sewer heat. Again, the sewer heat is only one small fraction of overall building heating, but it's neat technology. I think it might be a long time, maybe never, until we see the steam generating equipment that goes air to steam at any sort of commercial scale. I'd love to see it. I don't think it's high on people's priorities. So if you've got a steam system, you're probably replacing it. And honestly, once you get to where you can't use the pipes, because your steam, your condensate's the only thing size big enough to talk about the energy transfer. You are gonna be looking at different systems, and again, of that VRF variety is probably a likely. Last one, 2-pipe changeover system. So there was either the cheap version, you didn't run 4 pipes and you reused coils for heating and cooling, and you had a chiller and a boiler sitting on the line, and you just changed over. Winter was boiler, summer was chiller, and the in-between was somebody was uncomfortable all the time. Now it's only like 6 months a year, so I'm sure it's fine. That's a joke. Or water source heat pump sometimes used a chiller instead of a cooling tower. So this is an obvious, particularly for the water source heat pump, go into a heat pump chiller on that water source heat pump loop. So instead of a boiler, you've got a water source heat pump. You already were only going to make 90 or 100 degrees, so it's well within capacity. You don't need your cooling tower. You can run the chiller side. You can keep your cooling tower if you want. It might, it's a modest energy win. On the 2-pipe changeover system, where you ran heating loop in the winter at sometimes as much as 180 and cooling loop in the summer, you got to look hard at if a heat recovery chiller, also known as a air to water chiller, or air to water heat pump, they get different names. You got to look hard at, can it make the heating temperature, loop temperatures? Last couple slides. Ground source heat pump, I have to address it because I know that question's out in people's mind. I want a ground source or geothermal. I have trouble with that term, but it seems to be stuck. Sewer heat, other sources of heat, we got to talk about them. So ground source heat pumps are grand, and they have a big upfront cost, and every single analysis we've done on them puts them out at the shortest I've had is a 20-some year payback, and the longest I've had is more like a 40-year payback. It's a problem, but Duane mentioned PACE loans. You could use PACE loans for anything that's energy improving over baseline code, and ground source heat pumps certainly would be. That's a way to maybe put that cost on the building instead of on the books of the owner. Sewer heat, like I said, the amount of heat, low-grade heat that's going into the sewer is only a fraction of the overall building heat, but there's a lot of projects out there, and we're looking at our first one to do sewer heat recovery. I do expect that to be metered and sold like a utility if it's not already. It'll be jurisdiction by jurisdiction. But that'll start being seen as a resource, not just a free source of heat. So it's interesting. We tried to do a heat exchange with the Puget Sound and a ferry terminal we did. got told by the environmental folks on that project that it was impossible and that we shouldn't even try and pursue it. But you know, there are sources of heat like that. So we've got, like, if you've got a privately owned lake, you can do a geo loop. You get, give or take, 4 cooling tons per acre of surface area. We got to do, I guess, help rescue a winery that was using a geo loop for its heat exchange, lake loop. But be looking on your property if there's other sources. Those lake loops are super simple. It's some cinder blocks and you sink the piping down in the bottom of the lake. So you don't have to drill all those wells. Anyways, be looking for other sources of low-grade heat and heat sinks. You know, we're going to be getting a little more bold and a little more wild in the future. All right, last one. If you've got that, like I said, on the air side, the TSPR, total system performance ratio, it's your cooling load or your conditioning loads compared to your total carbon output. If your conditioning loads, because your envelope is crappy, is dragging you down, look hard at heat recovery chillers. That's one of the exceptions. I listed all the exceptions here. But exception 4 here, heat recovery chillers, you don't have to do TSPR. So if you have a envelope you can't comply and you're not going to, that's one way to use the exceptions to save yourself. Last word, and then C406 and we're done. So service water heating. Basically, if you've got gas water heaters, putting an electric water heater in a direct electric resistance water heater is a huge electric load and will increase your utility costs. If you do the unit to unit conversion, even though gas prices are way up, they're not up enough to make the difference. So same thing we've been saying in the hydronic side, we want to talk about heat pumps. And here's a couple options. So the one on the left is a tank style heat pump. It draws heat from the space it's in. For the HVAC designers out there, watch yourself, because we have had issues in small spaces, you know, where this will only operate down to 55 degrees, but it'll drop the room to 55 degrees before it goes to electric backup. So mind yourself what space you're in and what you can use with heat. Obviously, great if you can duct yourself to a server room where you've got essentially free heat. The one in the middle is an outdoor heat pump. Just like the hydronic version of air to water heat pumps, it has capacity limits at low ambient temperature, often requires a backup. And what we found in past projects is that they are extremely finicky on exactly how they are piped to things like storage tanks. So something to really get into with your rep, like if it's your first rodeo, make sure that you have gotten deep into it with your rep and maybe even called the company that you're, whoever you're using for the project. Last one, it's basically a CO2. It's a mini split condenser looking box, but it uses CO2 as a refrigerant, and then an indoor tank. So it slowly heats that indoor tank using a trickle heat pump. But because it's CO2, it can go down to super low temperature. The downside is right now it's 1-to-1. We don't have lots bigger equipment like that. So just like if you were doing split systems in a residential and you got 1-to-1 all over the place and a bunch of rooftop condensers, you'd have the same thing here. We have a bunch of condensers per water heater space. So it's really limited mostly to residential application. Duane didn't put this chart up, but I feel like it's important. I only spoke to HVAC and a little bit to water heating, but C406, you get some points for that. And when you're doing a TI where you're not really touching everything in the building, they've got to be on the table. Go into more efficient equipment. For the occupancies that allow it, go into higher efficiency service water heating. The lighting credits that Shaun's going to get into, you gotta put it on the table. All right, Shaun, any other questions?
I am not seeing any at the moment, but here's your opportunity. Questions, yep. Questions. Duane, I am going to make you the presenter while we're giving people a few moments to have any questions that they may want to have for Ben.
And I do want to say it one more time. We're I'm a practitioner, and we're all going to be practitioners for a while. And there's so many ifs and therefores that you just got to go read your code. That's how it gets done.
All right, thanks, Ben. I'm not seeing any other questions, so Duane, back to you.
So read your code. Are you saying people actually have to open up that big book? It's really...
I suggest they get a PDF and start putting bookmarks in. Personally, that's the way to get it done. But you know, if you need paper, sure, print it, and start getting your actual bookmarks out.
If we're going to be talking about that as a lighting practitioner, I will go ahead I mean, I've been doing lighting for 30 years. Every time I start a new project, I will skim the code again, because as Ben mentioned, it's impossible for anyone to keep everything in their minds. And particularly if we do projects in a variety of different jurisdictions, it makes sense to go ahead and skim the code that is specific to that jurisdiction. And I do it every single time.
Keeping yourself out of trouble. You know, the big delay when people are going in for permits is correction cycles. It's not the original review. The big delay, and if you come in with a set of documents that is really tight and have extremely few corrections, your client's going to love you. So we're going to leave the world of HVAC for a bit here and go into lighting. So the idea with our alterations thing is that the requirements are proportional to the scale of the work you're doing. So if you're just replacing fixtures, any more than 20% of them in Seattle, actually I think that's statewide now too, in any particular room or space, then you got to bring it all to that lighting power allowance, which means, you know, go to LED. The stage 2, if you're putting in new fixtures or you're recircuiting things, then you have to do all the local controls, so switches and daylight zone and aux sensors as required for that space. And then at the stage 3, you're actually messing with the lighting panel on the floor and putting out new raceway to the fixtures. You know, that happens once every 40 or 50 years. That then you'll also have to add in the automatic time switch, you know, which is more of a global thing. So each of those stages has the requirements appropriate to that level of work. We also have a controlled receptacles requirement in the code, and we have a list of room types that you need to have. That you need to have 50% of the outlets be controlled either with an automatic time clock or with aux sensors. So you see something like that little cartoon there with the one that is going to turn off on the weekends has a little symbol next to it. There's some exceptions here for alterations. One is that if it's less than 5,000 square feet, don't worry about it. And we picked 5,000 because that in Seattle is the threshold above which you have to have plan review for electrical submittals. If you're moving around your office cubes on the floor, you're fine. Any existing outlets in the existing walls, that doesn't matter either, and a few others. But for new outlets going into new partitions, you got to do that. Hello. For metering, we also have like a 3-stage thing. If you're doing a major HVAC alteration, which means completely replacing HVAC, or as we said, more than half of the heating and cooling capacity, then you're gonna have to meter the incoming gas and electric and submeter the HVAC, and then have the usual data acquisition and display system that you'd require for new construction. So that's stopping short of having you submeter any of the electrical stuff, but it's important. Then with that number 2 there, if you're just replacing an individual large piece of equipment, then you do need a local meter on that, local meaning that's the kind where you're going to have to go around with a clipboard and write down numbers if you want to check on that meter. But what it's doing is it's saying, well, over the course of 20 or 30 years, you will eventually replace all your equipment, and then you could hook those local meters up to a full system. And if you've got large gas coming into the building or into new equipment, you're going to meter that as well. And then finally, if you're doing an entirely new electrical system for the building, happens once in a great long while, then that gets the whole metering system required. So that was a quick introduction to the rules in the code. And now Mr. Shaun is going to take over and talk to you about how you do those lighting alterations in some reasonably economical manner. Starting with chandeliers.
Showing how it's done may be a bit optimistic in a very brief class like this. Before I switch myself over to the presenter back, I do have a question. For replacing equipment that is not planned but is showing signs of failure and hasn't failed yet, in an action of prevention, can it follow the like-for-like replacement option from the stated code requirements?
We said a piece of equipment is failing, not failed. And so, yes, you can replace one piece of equipment only that is failing. And like I said, that's not part of any kind of a larger project working on the system. It's not, it's you haven't just done another one of those in the very recent past. And so it's meant for an emergency situation. But people are very creative in finding ways to say, yep, this is failing. But so far we're not taking a super hard line on that.
Okay, so we're hoping that that people are honest when they're determining whether something is failing or not. Fair enough.
Well, the deal is that we had to have some kind of an emergency provision because you don't have hot water for your whole apartment building, or you don't have heat in your office, and it's the middle of the winter. That's a crisis. So we have to be able to deal with it, and then finding words to put in a code that try to enforce that is tricky. I'm certainly open to anyone's suggestions.
Fair enough. Are you suggesting that it's not easy to write codes for perfection? Unbelievable.
I'm working on perfection. I'm working on it.
You're doing a great job. One other question that's related on the same question, the 2018 SEC states that this is only for central equipment. Does that follow for service hot water as well?
Yeah, there's a similar thing for service. If you have an apartment building that's got individual water heaters in each unit, that would not be a central system. You wouldn't fall under that requirement.
All right, good enough, thanks. All right, let's talk lighting for a little bit. Lighting, and we'll talk a little bit of electrical. The good news from a code perspective is that those of us who have been dealing with lighting are pretty well acclimated, let's say, to dealing with changes with respect to the code from a lighting standpoint. Generally speaking, throughout the lifetime of energy codes, what that's meant is that every couple of years our lighting power density reduces. So, many years ago we might have used 2 watts per square foot, for example, for a private office. Today we might use 0.5 watts per square foot for a private office. Whatever those happen to be. The reality is, from the perspective of this class, however, let's face it, meeting these new lighting power densities is not a huge technical challenge for most projects, right? It's pretty straightforward. So when you're approaching a project, you're typically going to be looking at one of 2 things. You might have a simple replacement, right? That might mean that you simply replace your light fixtures or tubular LEDs, although we prefer fixture replacement from a designer standpoint, that will give you a better outcome over long term. So you might do one-for-one replacement, and I'll talk a little bit about that, particularly with respect to lighting controls as well, or you might do a redesign. We have an example here of a project that I did some years ago down in California, where I hope everyone will recognize the fact that this engineer, this is for a telecom company, spent a great deal of time creating this tent over his desk because the lighting was both too bright, too glary, and also, frankly, too much light, right? So this person spent a lot of time hiding from the light. So some questions to ask yourself as you're doing these things. Is your space overlighted? Is the distribution good? And is it doing what you need it to do? The reality is, particularly when we start looking at retail and office space and even hospitality as we go through some of these retrofits, people are not accepting marginal lighting the way they used to in a lot of places. If you've got a Class A office building, you better make sure the lighting is good. So when you're going ahead and doing that, consider a redesign. Now, if you have questions about how to meet the lighting power densities or all, please go ahead and send me an email. I'll be glad to offer you some direct thoughts, either at Shaun Darragh at seattle.gov or Lighting Design Lab at seattle.gov. And take a look at some of the resources we have available for you. We record all of the classes that we've been doing since the world stopped spinning in 2020. So there's a lot of recorded webinars out there. In particular, lighting audit and retrofit techniques are available for you. We did, Duane and I and some others did an entire 4-class series, 8 hours of content in the cost-effective code compliance series, so a lot more in depth than we can go in some cases here. Light sources, luminaires, lighting design process, and others. So I'm just going to give you a quick couple of obvious examples, and then we'll go ahead and jump into what I think is more interesting for retrofit projects, which is lighting controls. Seems to be a little more scary for people. So this is an example of an office that was a TI renovation that was done. This was done 5-6 years ago. So even 6 years ago, it was relatively easy to do a decent lighting job while still meeting the current lighting power density, right? So this is a software company that many of you have used their products on. And essentially, it's a complete redesign, right? We're using linear 4 or 6 inch aperture LED-based luminaires. The allowed per code energy code allowance here is 0.55 watts per square foot. The actual installed that you're looking at is about 0.42 watts per square foot, so significantly under the actual allowance that we have. But then we're also adding in lighting controls to essentially right size the light using something that we call task tuning that will lower that even further. And lighting controls are a big part of this stuff. A perhaps more prosaic example, it's not quite a one-for-one replacement, but Puget Sound Energy did a pilot study a couple of years ago with what we call luminaire level lighting controls. They weren't doing a one-for-one light fixture replacement. They actually did a somewhat redesign, but it's effectively the same kind of lighting, right? So we have recessed, in the original case, recessed 2x4 troffers. Now we have recessed 2x2 troffers. Now the difference is that we've added lighting controls, of course. We've added more light fixtures to make the quality of the light better for the people that are there. So we've gone from 67 2x4s to 100 LED troffers. And the connected load without dimming in this case is 0.56 watts per square foot. So actually slightly above the allowance, but with the difference between light fixtures from 2015 and the light fixtures from 2022, the improvements in performance will have made us go considerably below the 0.56 watts per square foot here. But the key thing to take away from this is that this is a retrofit that started with fluorescent lighting and basically minimal lighting controls, and by using luminaire level lighting controls, integrated light fixtures, made for a very simple retrofit project that would allow for meeting the current lighting power densities, saving a whole bunch of energy, and including the lighting controls requirements basically one for one with the light fixtures, saving a huge amount of energy, but more importantly, making the staff happier. That's going to be one of the things that you'll frequently hear from us, is that the non-energy benefits for lighting controls far outstrip the potential energy savings. It's important to consider that. So not gonna, like I've said, not gonna spend a lot of time on how to do lighting retrofits, because we're so far into it. We're 30 years into repeated cycles of doing lighting retrofits that, generally speaking, if you're using modern LED technology, the latest and greatest, you're almost certainly going to easily meet the code requirements. So let's talk a little bit about lighting controls. Lighting controls don't have to be scary anymore, right? From a standpoint of a renovation, it used to be complicated to do advanced lighting controls, right? To meet occupancy, vacancy, time scheduling, all these things, daylight control. We used to have lots and lots of different types of parts and pieces, and there was a lot of wiring and a lot of setup required. But we don't have to necessarily do those things anymore. Why? Because most of the time with lighting controls, we're actually using what we call networked or luminaire level lighting controls on our projects. You can still do the parts and pieces approach with respect to lighting controls of having relays that are talking to sensors that are kind of dumb devices that aren't really networked in any way, but that's not where the industry is going. So the key control strategies that you're absolutely going to have with respect to meeting the code when it gets triggered by the size of your alteration, you're certainly going to have manual switching, right? Every particular space is going to need to have the ability to turn the lights off. My suggestion would be that we put dimming in places wherever we can, since the light fixtures allow that. But you'll need occupancy or vacancy sensing, right? And of course, the difference between the two is that occupancy sensing, when you walk into a space, the lights come on. Vacancy sensing, you have to press a button. Now, generally speaking, the hardware is the same. An occupancy sensor or a vacancy sensor, the difference is usually a dip switch setting on the device or in the system programming. We're also going to have daylight harvesting, time scheduling. I don't have task tuning listed there, but task tuning, which is basically dimming light in given spaces to whatever the target light level happens to be, is an enormous energy savings, right? Generally speaking, lighting designers will overlight a space to accommodate potential design changes, but also to accommodate the fact that over time, light sources degrade, they put out less light. So if we task tune initially, so we dim down from, say, whatever the initial light level is down to the target light level, you can typically save 20 to 30% of the energy right out of the box. And that's pretty significant. So again, there are a variety of more in-depth resources that we have available for you at our recordings. In particular, fundamentals of network lighting controls. We'll go through all of this stuff in great depth, but there's also some 2-hour classes, network lighting controls value proposition, network lighting controls specific for healthcare, for schools. I think we have one also that I don't have here for warehouses. So those are all available to you. But at the end of the day, what we use, the network lighting controls that we have today, they're distributed. Normally the communication is wireless. They're easier to control, easier to install, more compatible with things, less costly, less complicated. In basically all ways, they're better than they've ever been before. In one of the, actually a couple of the classes that if you take a look at some of those resources, I actually detail out some of the costs with respect to retrofit projects. And I give you an example of a retrofit project that I did in my own offices when my offices were in the Bullitt Center. And the retail cost of the equipment for the pretty significant control package that we put together was about 75 cents a square foot. And that was a retail cost, right? That was if I bought all the parts and pieces from Amazon, literally. So we used to think of lighting controls as being fairly costly. Today, you can get a pretty good result for 50 cents a square foot if you really want to. So let's take a look at some of the mid-level systems, or some of the parts and pieces, if you will. I tend to think of mid-level lighting control systems as being spectacular for retrofit projects like this. Why is that? In the past, when we had to do lighting controls for retrofit projects, we would have to do a lot of rewiring. And that's costly, let's face it. If we have to bring additional pipe and wire down a wall to a switch box, for example, or we are adding additional wiring from light fixtures to control boxes to occupancy or vacancy or daylight sensors and whatnot, those become very costly very quickly. Today, we're looking at mid-level systems that are designed to be essentially a kit of parts approach, right? We start with the idea that the light fixtures themselves are dimmable, and then we add a variety of equipment that is really based predominantly on the idea of a load controller. Right, so the load controller is essentially a control device that wires in line with hopefully existing wiring. So you don't have to really change the wiring at all. You just hot neutral ground to it, and then you do whatever wireless, wired 0 to 10 volt controls to your light fixtures, and wireless control between the switches and the sensors. Goes up very quickly, goes up very easily, and the programming is typically done by smart devices, right? By your phone, by an iPad, stuff like that. Now, again, the key thing here is that you're talking about minimal installation, particularly if you're doing a one-for-one. You go ahead and use luminaire level lighting controls, and you'll have everything put in at once. We'll see that in a moment. But even if we're talking about using these load controllers, there's 5 connections, right? There's a line, a load, a neutral, and a ground, right? And then you've got the connections for whatever signaling control you're going to have between the load controller and the luminaire itself. So in most cases, like I say, you can just use existing wiring. Decommission whatever you have for lighting controls back at your lighting control panel. Make sure that you're constant hot in the lighting circuit, and then you're off to the races. Very, very easy. Now, one key thing about this that makes this so wonderful is that you actually have a lot less installation cost associated with wireless switches, wireless dimmers, wireless sensors than you have ever had before, because we don't have to run as much pipe and wire. We don't have to deal with things like touching up drywall, painting, all of these kinds of things. A lot of these devices are what the industry calls lick and stick, which basically means that you would have in some cases, even just double stick tape. Take an occupancy sensor, stick it up to the ceiling, and you're done, right? Then you just do a little bit of programming. And communication is via a variety of different methods and protocols: Zigbee, Bluetooth, an Ocean, Z-Wave, a lot of different potential ways to talk about that stuff. Now, I keep talking about this whole idea of luminaire level lighting controls. So this is just the idea that instead of adding load controllers and separate occupancy sensors and separate you'd still use the switches. Essentially, you take all the parts and pieces, put it into each light fixture, and within each light fixture, you just stick it up to the ceiling. Then you've got 3 connections to make up at each light fixture, right? Hot, neutral, ground. Everything else is part of the system, and it's logic. They'll have occupancy sensing and vacancy sensing and daylight harvesting already within the systems, and they'll actually come to the job site pre-programmed to a certain level. You'll want to go ahead and revise the programming and fine-tune it, but you have that option there. Now, again, as with everything else, we have lots of information, lots of resources that are available to you on our webpage, particularly with respect to LLC and network lighting controls. We have a variety of best practice guides, learning guides, some videos showing, and you can show your clients how these things work. Makes it very, very simple to get everybody on board, hopefully, with the same information. But this really does simplify the compliance with basically any lighting control requirements from any energy code I'm aware with, whether you're doing new construction or renovation construction. It's kind of the easiest way to do it. Another bit of thing that is useful for you, there's actually a pretty good study that was done by NEA, Northwest Energy Efficiency Alliance, in conjunction with University of Oregon, and they looked at the differences in cost and performance of one-for-one replacement for luminaires for retrofits specifically. So if you've got X number of light fixtures in your project and you replace them versus redesigning them with luminaire level lighting controls versus network lighting controls, there's some good costs there, and there's some good information. I do want to be clear that there is, of course, an additional charge for luminaire level lighting controls, right? Typically that winds up, depending on the system, being somewhere between $35 and $75, depending on the particular system you're using. And that's an upfront cost per light fixture. Now, that's offset by tremendous savings in installation costs. It's also offset by frequently utilities. We'll talk about utilities in just a moment. But if you're doing a retrofit project, lighting and lighting controls, please contact your local electric utility and figure out what is available to you as an incentive to help you bring your lighting and lighting controls to the next level, to what we really want it to be. Now, Duane had mentioned that one of the things that is out there with respect to the code is the plug load controls. Now, of course, this is not new, that we need to control 50% of the outlets. So a couple of good ways to do that. Whoops, I just hit my slide right. 1 second. A couple of good ways to do that. Some manufacturers offer smart devices. So they essentially have receptacles that are designed to work with their network lighting controls or their LLC systems, or they can be standalone as well. But the receptacle itself has a radio frequency receiver in it, and it will take signals from a wireless occupancy sensor or from a system that is time clock driven, and it will operate accordingly, right? So it will turn the lights on or turn the lights off. Another way to do that is with regular receptacles that are then controlled by a relay pack that looks an awful lot like, sorry, let me give you a spotlight, relay pack that looks an awful lot like one of these guys, typically 20 amp relays that will take signals, take commands from the system as required. Either way, just don't plug your CPU in, right? That's where most of the complaints come from with these systems. And the controlled receptacles have to be labeled that way, right? They have to be labeled that this is a controlled device. So don't plug any loads in that need to be permanently empowered. Now, Duane had mentioned also commissioning. Now, commissioning, in the lighting industry, we tend to talk a lot about commissioning lighting control systems, and we're being very, very loose with our language. Most of the time, what we talk about, or what we mean, is startup and programming. That's not commissioning, right? Commissioning requires a commissioning plan. It's typically a third-party kind of thing that involves reporting and functional testing of systems. Now, there are, as Duane had mentioned, hit or miss in the past compliance with respect to this. If you've done projects in California, for example, you'll find that the compliance is typically hit or hit, right? You have to do it. So assume that you're going to need to do commissioning of your lighting and lighting control systems here, and in fact, other electrical systems as well. Now, from a lighting standpoint, the Illuminating Engineering Society has this DG 2911, which is a very good document that lays out all of the steps in a very cogent flowchart manner to be able to tell how you go about doing some of this commissioning. But as Duane mentioned, make sure that you've got some dollars in your budget for a commissioning agent and for hopefully bringing the commissioning agent in early into the project so you can start to look at things like sequences of operations. You know, we've had this idea of sequences of operations for HVAC systems forever, right? We need to be doing this for lighting controls as well, right? What are the time schedules? Which sensors are occupancy or vacancy? What are the timeouts? What are the target light levels? How are the switches and dimmers configured? How is the daylighting system configured? What are the daylighting zones? All of these things are important, and they really need to be figured out beforehand, right? And they need to be delivered in a very cogent manner. This can typically be either in matrix style or in narrative style. If you go to some of the resources that I'd sent, particularly my networked lighting controls classes, go to those recordings. There's a great deal of information about that there. Now, also, as I'd mentioned, utility programs, right? I work for Seattle City Light. In the city of Seattle, Seattle City Light, of course, is our utility. We have lots of opportunities for the utility to help you with these retrofits, right? Training like this, for example, we've providing case studies, some of the things I've given you in the knowledge base. We also provide incentives in a lot of different ways, right? So for example, luminaire level lighting controls, if they're qualified by the DLC, the Design Lights Consortium Qualified Products List, will typically yield you a $75 per light fixture incentive in order to use luminaire level lighting controls. So generally speaking, that means that you are going to get your lighting controls more or less paid for if you do it right with Seattle City Light. Now, other utilities, Puget Sound Energy, for example, have similar programs. This is actually becoming a very big deal with respect to electric utilities as they're realizing how much energy can be saved that way and how much better our projects can be. Now, the last thing that that Duane had mentioned was the idea of metering. I'm going to tell you that I am not an electrical engineer, so I'm not going to go into the very specifics of how metering goes, but I will say take a look at C409, energy metering and energy consumption management, right? This will give you some sense that you're going to need, depending on what part of the code gets triggered, you're going to need to add metering for a variety of different energy sources, right? And energy uses, lighting, plug loads, various electrical elements. If you're adding on-site renewables, for example, right? If you're adding solar cells, you'll need to have some level of metering. And you're typically going to want to start to be doing things like data aggregation into dashboards, right? And storing that data so that it can be used for trending, it can be used for things like this. A lot of the projects that I've done in the past number of years, we've actually gone ahead and developed energy use dashboards, right? So that I used to think of them as sort of the modern weather station for buildings, right? Old buildings, we used to walk into the lobbies and there'd always be a weather station telling us what the relative humidity was. Well, now we walk into a lot of buildings and we see dashboards that tell us what kind of energy performance our building is providing, right? And I've found that tenants tend to like to see this kind of information. When you let people know why you're doing things, they tend to approve of them. So with that, I am going to say, does anybody have any questions before I hand this off to Duane to talk a little bit about building envelope, and then we will go ahead and go back to the final questions. Any questions? Duane, I'm making you a presenter while, oh no, I'm not gonna do that. I'm gonna keep it controlled. Sorry, I forgot. So any questions? I'm not seeing any. So Duane, why don't we go ahead with, you do need a permit for re-roofing.
Yeah, well, just wanted to mention a few things about envelope here. It used to be that re-roofing of any kind was given a pass on, and since we're in an alterations seminar, I just wanted everybody to know that when you do a roofing project over 500 square feet or something other than a single family, you do need to get a permit for that. And the reason is that we want to make sure that people doing re-roofing projects are also complying with the energy code requirements. Advance, please. So I'm not going to explain every cell on my little chart here, but just note that there's kind of complex relationship of where full insulation or partial insulation is required. And in general, if you're doing if you got a conventional sort of flat roof building with roofing on top of the deck and insulation or no insulation on top of the deck, that's going to need to get insulated, and that does get complicated. We recognize, and we'll work with you on it. Otherwise, we'll send out the slides later. I'll let you look at the different cells in this, but I was tried to graphically explain where we're at. Next, please. So there are a number of exceptions. So if the neighborhood kids knock a ball through your window, you can replace that. You can if you're doing some kind of work that opens up the cavities in your wall or ceiling, you got to fill the available cavity with insulation, but not go all the way up to the code requirement. If they didn't expose any cavities, you just leave them alone, uninsulated or whatever. If you're just putting a new door into an existing opening, then you don't have to do the vestibule. And finally, air leakage testing, you're not going to have to do unless you're in one of those big categories. Next, please. So air barrier testing, like I just said, is not going to typically be required in alterations. And the reason is that if you're not doing the entire envelope, then air barrier testing would be a little bit silly. So if you're doing a substantial alteration, where we occasionally see this in Seattle, that they've actually stripped everything off the studs and kind of going back to the bones, then you'll do that, or for one of these other major categories, but otherwise not. Next, please. And that was it for the technical part of our presentation. Shaun, why don't you take back over again?
Ladies and gentlemen, this is your last chance to offer up questions to us. So please go ahead and type in your questions. I'm going to give people a couple of moments to go ahead, and I see we have one now, but I'm going to give people a couple of moments to go ahead and enter in some additional questions, thanking Duane and Ben for being here today. While the questions are coming in, I am going to give you a couple more things. One, this is of course one in a series of many educational opportunities. Next week, I will be teaching network lighting controls for healthcare. So I'll be talking about some of the very specific issues surrounding healthcare and network lighting controls. Then we switch over into some stuff that is particularly germane to mechanical engineers, commercial heat pump water heaters for hospitals and clinical settings. Then we jump into energy management systems, part 1 and 2, commercial refrigeration, part 1 and 2, and adjustable speed, variable speed frequency drives, parts 1 and 2. So those are all coming up. The dates are there. Typically, they'll be about the same time that we are now, which is Thursdays from 10 to noon. Note that there are a couple of them that will happen in the same week. That will be Tuesday and Thursday, 10 to noon. And of course, the slide deck will be available to us from when I put this stuff together. So in a few days, the recording will be available, the slide deck will be available. If you have questions, please go ahead and send us. Ben, apologies that I didn't put your email on this particular slide. But also, of course, feel free to poke around in our webpage, the Lighting Design Lab. We have a lot of educational and various resource materials available there. And we are presented by Lighting Design Lab and Seattle City Light. So while that is all there, let us go back to questions. So the first one, what about air barrier testing requirements for additions? Duane, I think you answered that, but go ahead and let us know if there's anything else.
You do have to test the air barrier for an addition, and which typically means that you've got to somehow separate the addition from the existing building. What we found is that people who think about this during the design phase can think of how they can put up a temporary barrier or something to make that go. People who did not and who are trying to make that happen at the last are having a really tough time. But yeah, you got to test the new addition air barrier.
Okay. Next one, Duane, this is for you. I have specific energy code interpretation for fan efficiency energy calculations from manufacturer available data as it relates to a laboratory space. Duane, are you the right person at the building department to discuss this further with?
You can send it through me, but it would land at our we have a staff of 6 mechanical engineers that do energy and mechanical review, and they're the ones that would handle that. I confess I'm an architect, so there's a lot of things I don't understand.
Okay, fair enough. Any guidance on how to sell executives on a large chiller replacement project to go with heat recovery chillers, even though it leads to increased utility costs due to cost difference between gas and electricity? Ben, I see you laughing. Is that one you want to take?
Yeah, that can be a challenge. So it's on future promise of less pain. You need to do long baseline life cycle cost analyses because gas prices. I saw a study last week on the Maryland side of the country that said that natural gas prices in the next 2 decades are going to go up by a minimum factor of 5 and by a maximum factor of 10, while electric prices go up by a factor of 2. And so that chiller you're putting in now is going to last 25 years. And if you're talking about heat pump instead of a gas equipment, particularly on the heat pump cycle, if you're getting a COP of 2.5 or 3, in today's dollars, you're paying similar utility rates because of the efficiency of natural gas is 80%, and that COP of 2.5 or 3 is 250 or 300% efficient. So first, do the math in today's numbers, but if it doesn't quite pencil out, if it's much more capital cost and you're like, you're gonna spend a bunch and your utility rate will be exactly the same. That's not the greatest message, I agree. But if you do it on a life cycle basis and you take real escalation rates that are separate for electric and gas, which not all life cycle cost analyses take separate rates, but gas and electric are gonna diverge. Pretty darn sure about it, particularly if we start putting carbon taxes out there. So if you get real about that, do a 20-year baseline life cycle cost analysis. I guarantee the heat pump chiller is wildly attractive.
And I could add to that both the International Energy Information Administration and the World Bank predict about an 80% rise in gas prices over the next 8 years, and also there's some political things going on that make that even more interesting. And if Seattle is indeed going to be putting our carbon emissions factors on top of the building performance standards, you might, if you do a new gas system right now, you might end up taking that out in 5 years.
Okay, I'm going to pause this for just a moment. It is now basically noon. Any of you who need to jump off, we certainly recognize that. We will keep answering some questions here. But for those of you who do need to jump off, thank you very much for joining us, and we will see you next time. So now, with that said, back to questions. You guys can both stay for a few minutes, right?
Yes.
Yeah, I got a whole half hour if we need it.
Sweet. So then one question here is, Ben, can you share a link to that study?
I can tell you how to Google your way there, because I apparently can't link to everybody, but it's the Maryland Commission on Climate Change. It's the building focused appendices. It's right on their cover page. If you go to the Maryland Commission on Climate Change, over on the right, it'll say yearly report, and then it'll say appendix in a teeny little print down below. You want that appendix that has a study from E3, who's a real thought leader in this space. And that E3 study shows a bunch of graphs showing different escalation scenarios. It's super geeky, and I had a lot of fun.
Well, fantastic. I will throw out there from it's not a boiler replacement, but from a convincing people to kind of let's just say do the right thing. I've found that getting people to understand, or trying to get them to understand that you know, when we're in a world where we're seeing 100-year events every 5 or 10 years, and that's accelerating, and we're in a world where potable water is about to become a big premium, and we're killing some of those aquifers by fracking. I'm thinking that electricity is probably a pretty good bet. So,
so to hospital administrators, if it didn't work to appeal to their long-term pocketbook, and it didn't appeal to a term to their appeal to their sense of fairness, you can also appeal to their sense of the press release, because a hospital that degasifies and goes all electric right now, that is a media splash. They would have a big field day with that.
All good stuff. So for electrification projects, we've been told by code reviewers that new building permits are required to get the reviewers to review the calculations showing that the heat pumps will use less energy than existing gas equipment. Does the new change in space conditioning guidance require pulling building permits for mechanical projects? I can repeat parts of that and unpack it if necessary.
I do understand.
Pacific, we should start there.
I do understand the question, and no, I can't see why you'd need a building permit. They're asking for some modeling to be done, either modeling or some other convincing calculation that would show. But we've had a few of these come across, and they've been easily able to demonstrate that they're using less annual energy by quite a ways. Okay, any other questions? Going once, going twice. We've got a few thanks here. Thanks for the good information. Give people another 20 seconds or so to go ahead and put in any other questions. Again, we tossed a whole bunch of information really fast at you. And if you want to see more expansive, specific information about any of the new requirements, envelope or mechanical or electrical lighting, go ahead and go to the Lighting Design Lab education page, and you can look at the 8 or so hours of scintillating information that we've compiled there for you in the last couple of iterations of the new energy code stuff. So those, of course, are not specific to alterations, but will give you more in-depth information than we've been able to give you in just a 1-2 hour session. All right, any others, any others, any others? I am not seeing any more. So with that, then I will say, as some folks have said, that's all, folks. So please go ahead and take the survey. Let us know what's been helpful, what may be more helpful for you in the future. And with that, signing off on behalf of Seattle City Light and the Lighting Design Lab, thank you, Duane. Thank you, Ben.
It's been a pleasure as always.
Thank you, Shaun, and thanks for everybody. Keep in touch.
Thank you for having us, and enjoy reading your code. Yeah.
That seems optimistic. You guys have a great day.